In the previous lesson, we have seen that for linear models, it is very important to check for the basic assumptions. Indeed, what we always do is this. First of all, we need to fit the model. Then we calculate the residuals from the model fit. That is the difference between the observed values and the predictions from the model. Then we take the residuals and we inspect them to check whether the basic assumptions are met. You may remember that the basic assumptions basically refer to the fact that the residuals are distributed as following a Gaussian distribution, and that the residuals are homoscedastic, meaning that the standard deviation is the same for all groups if we are talking about ANOVA models. In order to inspect for the basic assumptions, we have both graphical and formal methods. In particular, the graphical inspections of residuals is based on plotting the residuals in different ways, for example, against the expected data, or, for example, against quantiles from a normal distribution. We also have formal procedures, for example, the Bartlett's and the Levine's test for homoscedasticity, or the Shapiro-Wilks test for normality. In the previous lesson, we have seen an example. The example was regarding 15 independent leaves of tobacco that were treated with 3 insecticides, 5 leaves per insecticide. 10 days after the treatment, the number of living insects was counted in each leaf. And the results were this. So you see we have 3 insecticides, the insecticide A, the insecticide B, and the insecticide C. Basically we have 5 leaves, 5 replicates for each insecticide, and these are the counts. And we have the mean count, which is reported here for the 3 insecticides. And we see that there is a big difference between the highest count and the lowest count. It is 1 order of magnitude. And furthermore, you can see that the standard deviation are really very different. So here we have 191. Here we have 25. So it's again almost 1 order of magnitude. And above all, these are counts, and we should not expect that counts are normally distributed because they are discrete and they cannot go below 0. So in this case, we are highly suspicious about the basic assumptions for fitting linear models. So we expect that the residuals may not be Gaussian and may not be homoscedastic. So let's basically recap how we decide whether these data obey to the basic assumptions for linear models. So we switch to R together, and then we clean everything. Basically, we don't need to clean because everything is very clean at the moment. But as a habit, I always clean my workspace. Then I load the data. So the file name, including the path, is https://www.casaonofri.it/datasets/insects read.csv. So this is the name and the path of the file I want to open. You see it is a CSV file. So we read it by using we create the object dataset and read it by using the function read.csv. And we show it. So in this case, we have 3 treatments, T1, T2, and T3. They correspond to A, B, and C in the slide. 5 replicates, and the observed counts. So we first fit the model. We could do some data description before, but you see this is not, we don't do it now. We take it for granted, assuming that we have already described the data set. So we feed the model, and it's an ANOVA model because the predictor is the insecticide and it is a factor. And the response is a count. So basically we can feed the model like this. Create a new object, use the lm function, and express the count as a function of the insecticide. And we also say that we take the data from the dataset object. So we feed the model. And then we inspect the residuals. First, we can plot a graph of the residuals against the expected. We use the function plot and set the argument to which to 1, which gives us exactly the plots of residuals against expected. And we see here that we have a really evident funnel shape. So the residuals do not appear to be homoscedasticity. No homoscedasticity, indeed. And if we plot the QQ plots of standardized residuals, which is obtained by setting the which argument to 2, then we see sensible deviations from this line here, which would correspond to Gaussian residuals. Residuals are not Gaussian because they do not lie above this dotted line here. So, no Gaussian residuals. They are probably log normal instead of normal, but we don't mind. So, as we did last time, we come to know that the basic assumptions for linear models are not met in this case. What do we do if the basic assumptions are not met? We have not talked about this last time, so we now should see how we should behave in this case. So, if the basic assumptions are not met, and if we go ahead without doing anything, we have a problem because all inferences we do are based on the wrong probabilistic model. So they are based on a Gaussian homoscedastic model. But we see that the real model is not Gaussian homoscedastic. So we would be drawing conclusions based on the wrong model. And consequently, confidence limits do not have the right coverage. They are not correct, and p-levels are not right. So, if we reach conclusions based on the wrong model, simply these conclusions are not reliable for our data. So we have to do something. And what is the easiest remedy for violations? The simplest solution, as you see, is to make a so-called stabilizing transformation. So I take the data, I take the response. If the response is not okay in the original scale, I change the scale to a new scale where the basic assumptions are met. So we transform the data to make them fit to our model. Of course, we also have other solutions. For example, we change the model to fit our data, but these solutions are more complex. And so we prefer to transform the data to fit our model. I mean, this is perhaps not the most modern solution, but it is still very used, for example, outside the university, in industries, and several practitioners still use this simple solution to the lack of basic assumptions. In other words, we look for a new metric where the basic assumptions are met. For example, this is interesting. You see that this graph has a funnel shape, and these are the residuals here. For a small response, expected response, the residuals are very close. For highest observations, for highest expectations, the residuals are very high on average. So it would be interesting to take the scale of the residuals and expand it here so that we make the residuals more distant from one another and compress it here so that this graph loses funnel shapes and becomes more random. What can we do to alter the metrics? For example, we have the logarithmic transformation. The logarithmic transformation, you see here the scale in the logarithm, and you see the corresponding value in the natural original scale. Here we have -3 in the logarithmic scale that corresponds to 0.001, -2 that corresponding to 0.01, -1 corresponding to 0.1, 0 corresponding to 1, and so on, 1 corresponding to 10, 2 corresponding to 100. This is the decimal logarithm. So you see that here we have the same distance here from 0.001 to 0.01, same distance from these two values here that we have from, for example, 3 and 4, which correspond to 1,000 and 10,000. And the same distance from 1,000 and 10,000 then from 10,000 to 100,000. So you see that we are compressing the scale here and expanding it here. So exactly what we were doing here. Expanding small values and compressing high values. So the logarithmic transformation is a scale, brings us to a new metric where perhaps the basic assumptions are met. If you look in traditional stat books, you will probably find a lot of transformations that are suggested for certain types of data. For example, logarithmic transformations are always suggested for counts as well as square root transformation, which are also recommended for counts. The arcsine square root transformation is recommended for proportions. Basically, we have a set of recipes from where we can select the most correct transformation. This is one possibility. I mean, I have a certain data set, and depending on the characteristics of this data set, I select a certain transformation. Or better, I could use the so-called Box-Cox family of transformations. Here we have two possible families. For example, this one. This is a transformation where the transformed value, that is W, is equal to the original value y raised to power lambda. Lambda is any value from minus infinity to plus infinity. If lambda is equal to 0, this transformation does not make sense, and we use this transformation here. So we take the logarithm of the response. So here, the response rises to power lambda, but if lambda is equal to 0, then we take the logarithm of the response. This transformation here is totally the same as this transformation here. What changes here is that I take, when lambda is not equal to 0, I take the response rise to lambda, I subtract 1, and I divide by lambda. So these two transformations are very similar in terms of, the results I would obtain by fitting a linear model. But this transformation is easy to understand because in this case, the logarithm of the response is the limit of this expression for lambda that tends to 0. So this explains us why when lambda is equal to 0, we take this expression here instead of this one, which has no meaning because we cannot take a number, we cannot divide a number by 0. So basically these two transformations are very simple. So we can just take this one instead of this one when lambda is not equal to 0. Box and Cox, so you see here that for this family, by changing the lambda value, we obtain several different transformations. For example, when lambda is equal to 1, then we take the response, we rise to power 1, so we do not transform at all. If lambda is equal to 0.5, then we take the square root of the response. If lambda is equal to 0, then we take the logarithm of the response. If lambda is equal to minus 1, we take the reciprocal of the response. So if lambda is equal to 2, we take the square of the response. So you see that we can, by selecting lambda, we can make a lot of different transformations. And Box and Cox taught us how we can calculate the likelihood for the transformation. For example, we can take lambda value changing from minus 2 to 2, fit the model, and by using the method proposed by Box and Cox, we can calculate the likelihood of the model. So you see that the likelihood goes up, it reaches a maximum value, which corresponds in this case to a lambda value of 0.1 approximately. Then the likelihood goes down. So it is very easy now to select the best lambda value. We take the lambda value which maximizes the likelihood of the model, the better the likelihood of the data under the transformed model. So in this case, lambda would be equal to 0.1, but using lambda equal to 0.1 is not really very common. So it is interesting to look at the confidence limits for lambda, which we can see here. This is the lower limit, and here this is the uppermost limit. Basically, it means that any value of lambda from minus 0.1 to roughly 0.5 is okay to transform the model. Within this range here, we select a lambda value which corresponds to the most common transformation. For example, the logarithmic transformation is very common in literature. So here we could select a logarithmic transformation. So let's see this with our data. I need to load the library mass and use the boxcox function and pass the model object. So I obtain the likelihood of the model depending on the transformation. And from here, I can understand that using a logarithmic transformation is okay for this data set because 0 is within the confidence limits for lambda according to the box and cox procedure. So we have selected the transformation and we have some evidence to support our selection, which is okay. This is an interesting technique. For example, in some cases, 1 might be included in the confidence interval, which would tell us that we don't need any transformation at all. So you see that we can use this procedure also to understand whether a transformation is really needed. In this case, it is needed, and so we need to transform the data and refit the model. So I'm taking this model, copying the code here, and then model to change the model. Instead of taking the count, I take the logarithm of the count and fit the model again. So one can now inspect the model here, and you see that now the fennel shape has disappeared, and it looks much more normal, much more homostochastic, I mean. So, and I can also look at the Cook plot here, and we see that we are much closer to the dotted line. So we are in this metric, in the logarithm, the data seems to be more amenable to fitting a linear model. So we take this model instead of the previous one. Okay, in this case it looks as if we have found a suitable transformation, and therefore we simply do the analysis as we would do normally, and in practice we make the variance partitioning on the transformed data. So we use the function ANOVA and pass the model which we fitted on the transformed data. And we see that that this is highly significant. And now we can conclude that we can reject the null hypothesis that there is no difference between the 3 insecticides. Indeed, we can accept the alternative hypothesis that at least one insecticide is different from another one. Now we can see here that the boy is happy because the new analysis give good results, and we have no problems with the basic assumptions because we have worked with the logarithms of the counts. Now we make some conclusions. Whenever the data do not conform to the basic assumptions, we need to find a suitable transformation, or we need to transform the data, and we need to repeat the analysis on the transformed data. This is a very simple path which we can use every time. Of course, some problems may arise in later stages, and in particular when we will have to discuss the difference between the means, but we will come back to this problem later. So far, the lesson is over. Thank you for listening.